So we'll continue in this chapter with the chapter of equilibrium of other reaction classes, and in this video we'll be focusing on how we can predict formation of a precipitate of a particular salt. So for a precipitation reaction, you guys hopefully remember a precipitation reaction is when two different solutions are mixed together such that a precipitate is produced, or an insoluble salt actually precipitates out from the salt solution. So how can we predict if a precipitation is going to happen after mixing two salt solutions or not? That would be if a solution is a completely saturated solution for a given salt, QSP value is going to be equal to KSP. And hopefully you guys remember that expression for QSP is exactly same as the expression of KSP. It's just that the values of the two constants might vary. So KSP value, if KSP value is equal to QSP, the solution is going to be saturated and we would not see a precipitation reaction happening. However, if QSP value is greater than the KSP value, a precipitate will form until the remaining solution is saturated. So whenever QSP value is going to be greater than KSP, it's exactly same concept as we have seen in chemical equilibrium when comparing if a reaction goes towards left or right. So it's the same concept. If QSP is greater than KSP, a precipitation reaction will occur and insoluble precipitate will be formed. If QSP is less than KSP, then no precipitate will be formed because the solution is still unsaturated. So if a question asks after mixing two different solutions, is a precipitate going to be produced or not? How can we tell the answer? We'll have to basically calculate QSP values and compare those to the KSP values, and depending on what values we have, what is the relationship, we can make a prediction if it's going to precipitate or not, or if it's a saturated or an unsaturated solution. So let's take a look at a couple examples here. One form of kidney stone is calcium phosphate. So this is the equation or the formula for calcium phosphate, which has a KSP value of this. How can we tell if a salt is insoluble? The easiest way is if KSP is given to us for that particular salt, we know that it's an insoluble salt. A sample contains this much molar calcium ions and this much molar of phosphate ion. Predict whether calcium phosphate will precipitate or not. So this is a straightforward question where for a salt, the concentration of the cation as well as the anions are given to us. We just have to figure out if it's going to precipitate out or not. So to compare the KSP and QSP values, we'll first have to figure out what is the QSP value for this. KSP is given to us. So if it's calcium phosphate, let's begin by writing our reaction for dissociation of calcium phosphate. You don't have to necessarily write it if you understand that each calcium phosphate salt is going to give us 3 calcium ions and 2 phosphate ions. So essentially our Q expression for QSP in this case is going to be concentration of calcium ions cubed, oh my bad, times the concentration of phosphate ions squared. So in this case, since we have the value of these concentrations, we can just plug in the value straight up. Calcium is 1.0 times 10 raised to power minus 3 molar cubed times phosphate is 1.0 times 10 raised to power minus 8 squared. And if we solve for this, this would give us a value of 1.0 times 10 raised to power minus 25. Now based on this, we can clearly see that our value of QSP is greater than the value of KSP. So QSP here is greater than KSP since our KSP value is this. So based on this, if the value is higher, we can say that this is going to create precipitate of calcium phosphate. Right. Let's look at another. Okay, so let's try another example. A common lab method for preparing a precipitate is to mix solutions containing the component ions. Does a precipitate form when 0.10 liters of calcium, 0.3 molar calcium nitrate is mixed with 0.200 liters of 0.06 molar sodium fluoride? KSP of calcium fluoride is given to us. So this is a kind of question, other kind of question that we can get to predict if a precipitate will form or not. So in this case, what's happening is that we're mixing two different solutions to actually prepare a precipitate. And the question is, if I mix this much amount of these two solutions, is it going to precipitate the salt or not? So the first thing is, when you're mixing two different solutions, you should be able to identify what is the salt that is going to be produced. One approach is that we write down the equation. So we are mixing calcium nitrate, which is an aqueous solution, so it's a soluble salt because all nitrates are completely soluble. The second salt we are mixing is sodium fluoride, which is also a completely soluble salt. They will interact with each other, and if you guys remember, double displacement reaction. So this is an example of double displacement reaction where the ions displace each other and take their position. So sodium is going to create a salt with nitrate, which is sodium nitrate, and fluoride is going to react with calcium to form calcium fluoride. Now nitrate, again, all nitrates are soluble, so this is aqueous. Calcium fluoride on the other hand is the solid here. So one way is that we write the reaction and figure out this is a salt that will precipitate out, and we have to figure out if this is going to precipitate or not. The second easy approach is KSP value in question is given to us for calcium fluoride, which means we are interested in this salt. This is the salt that is going to precipitate, right? Once we know which salt we're interested in, if you want to predict if it's going to precipitate or not, the question is simple. We have to first solve for QSP. What is the value of QSP? And then compare it to KSP value. So QSP for calcium fluoride is going to be concentration of calcium ion times fluoride ion squared. So if I can solve for both these concentrations, I can solve for QSP. Now, important thing here is that these concentrations that are included in the QSP expression are the final concentrations of calcium and fluoride after mixing. Okay. What's given to us in question are the concentrations of calcium coming from calcium nitrate and fluoride ion coming from sodium fluoride. These are initial concentrations. So we'll have to figure out what would be the concentration for each of these after mixing. How do we know that? We know how much of calcium we mixed, right? Each calcium nitrate salt mole is going to produce 1 mole of calcium. So we can figure out how many moles of calcium were produced from here. That would be, if I can figure out moles of calcium that were mixed calcium ion, would be molarity times volume, right? Molarity is, sorry, molarity is 0.30 molar times volume 0.100 liter, right? That is moles of calcium. And what would be the final concentration of calcium? This is final after mixing. That would be moles over the final volume. Final volume is 0.200 plus 0.100 liter. So it's going to be moles, which is, I just figured out, is 0.30 times 0.100 liters, and final volume is 0. This plus this, so 0.300 liters. That would give me the final concentration of calcium. Similarly, I'll solve for the final concentration of fluorine or fluoride ion. Once I have these two values, I can plug it into this expression and calculate QSP. So right here, The calcium concentration comes out to 0.10 molar. Similarly, we'll figure out what is the moles of fluoride ion, which is 0.060 times 0.200, which would give us these many moles. Now, moles divided by the final moles, which would give us 0.040 molar fluoride. Now, to figure out QSP, we plug in the values into this expression right here, and that would give us a value of QSP of this. So now if we compare it to the KSP value given to us in question, QSP value is higher. QSP is greater than KSP, which means calcium fluoride will precipitate out into the solution. Okay, let's try one more question. I'll leave you guys with this question. So this is very similar concept. Will a precipitate of lead iodide form if 100 ml of 0.05 molar lead nitrate mixed with 200 ml of 0.100 molar sodium iodide? So KSP for PbI2 is given, meaning we are interested in this salt, right? So if we want to figure out will a precipitate form or not, we first have to solve for QSP. QSP for this salt would be concentration of lead ion times concentration of iodide ion squared, right? Now where is the lead coming from? Lead is coming from lead nitrate, so right here. And iodide is coming from sodium iodide, so concentrations are right here. So same concept, I need to figure out what is the final concentration of lead in this solution. For that, I'll first solve for moles of lead and then divide it by the final volume of solution, which is 300 ml in this case, to get the concentration of lead. Similarly, we'll solve for concentration of iodide and calculate KSP. So I'll let you guys solve for this question. Once you're done, you can compare your answer right here. So initial moles of lead would be, you can convert this into liters. What's solved here is in a different unit, but the easiest way is that you convert everything into liters, solve for the number of moles divided by the final volume, which is exactly what is being done here. So don't get confused with the units. That would give us the concentration of lead. Similarly, we'll solve for the concentration of iodide. Again, please don't confuse with these millimoles and milliliters written in here. It's essentially what we're looking for is moles divided by volume in liters. So you should work with the unit that you are familiar with. So moles would be molarity times volume. Molarity is given to us times volume in liters. So make sure you convert the units. You don't get confused with the units that you see here on the slide. It should finally give you the same number if you're doing it all correct. So once you solve for iodide, the concentration will come out to this right here. We are going to plug in these values into QSP, and this is our QSP value. And the final step is, if we want to figure out a precipitate will form or not, we compare QSP with KSP. KSP is given to us in question, and right here we can see that Q is again greater than KSP, which means the precipitation will occur in this case as well, right? Hopefully everyone understands it. It's not too difficult. So now finally I'll just move on to a very easy idea or easy concept, which is again based on Le Chatelier's principle. So up until now we were talking about few salts. So now let's talk about some salts, solubility of some acidic and basic salts. So for acidic salts, most of the salts usually that you would see that are acidic are containing ammonium ion. And ammonium, if you remember from again the solubility chart, most of the ammonium salts are usually soluble. So most of these times you would not see very many insoluble salts containing ammonium ion. So that's why acidic salts, you might not see many questions regarding that. But when it comes to basic salts, Most of the basic salts, the anions, you guys are familiar with. Anions come from the weak acids and they are the conjugate bases. So if we add, now let's say if I have a salt and I add more hydronium ions or protons or acidic, more acid solution into that, what would happen to the solubility of these salts? Most of the cases it is going to increase the solubility of the salt in case if it contains anion of a weak acid. That is what's important here. If the salt consists of anion of a weak acid, when we add externally we add acid into the solution, it is going to increase the solubility. And how does it do that? It's again based on Le Chatelier's principle. So let's say look at example of calcium carbonate. Calcium, we know it comes from the cation. This comes from calcium hydroxide, right, which is a very strong base, so that makes this a very weak conjugate acid. So this is not going to be affected when we add acid solution from outside. But carbonate, on the other hand, comes from carbonic acid, which is a weak acid, so that makes this a weak conjugate base. So we know that calcium carbonate has an dissolution or solubility of calcium carbonate will be in this equilibrium. So calcium carbonate dissociates to give us calcium ion and carbonate ion. Now if I add some acid from outside, it is going to disrupt this equilibrium. How? Acid is going to react with carbonate because carbonate is a weak conjugate base, like we just figured out. So this weak conjugate base is going to react with the acid, which is H3O plus, or you can simply write it as H plus, same thing, would give us some bicarbonate ion and water. This bicarbonate ion can further react with more acid to produce carbonic acid, which can later on be converted to CO2, water, whatever happens at the end. But ideally what we are seeing is that H ion is going to react with this carbonate, meaning it's going to reduce the concentration of one of the products. When the concentration is reduced of the product, the reaction tries to do the exact opposite of that, and it will try to produce more product by shifting the equilibrium towards the product, right? So this is again based on the Le Chatelier's principle, and that's why more and more calcium carbonate, the more it goes towards the product, more calcium carbonate will become soluble. So that's why it says whenever you add acid to any basic salt solution, it is going to increase the solubility of that acid. Okay, let's take a look at a couple different examples for in this case. For instance, if I have a salt solution of magnesium hydroxide, it's insoluble. It's going to solubilize to produce magnesium ion and hydroxide ion. Now what happens if I increase the hydroxide ion concentration? Hydroxide ion concentration means I'm adding more of the hydroxide ion, right? So if I'm adding more of this, the reaction will try to reduce the concentration, so the equilibrium will shift towards left, correct? On the other hand, if I increase the proton concentration, what will the proton do? Proton will react with the hydroxide ion concentration, right? So it's going to reduce the concentration of hydroxide ion. As it reduces the concentration of hydroxide ion, reaction tries to oppose that and increase the concentration of hydroxide, which means the reaction will move towards right. Okay, so these equilibrium can also be written in terms of if it's going towards left, it means that we are decreasing the solubility of the salt, right? Because more of it is going to be precipitated out. If it is going towards the right, meaning more and more of this is going to be solubilized, so it is increasing the solubility of our salt, correct? So let's look at another example. If I have silver phosphate, which is again insoluble salt, produces silver ion, phosphate ion after solubilization. So this is the equilibrium of reaction for the solubility of this salt. What is the effect of adding proton on the solubility of silver phosphate? So what is the proton going to do? Remember, protons, if we add more acid from the outside, it only reacts with the anion for basic salts or anion that comes from weak conjugate acids. Okay, remember that. So silver again not going to be affected. Phosphate on the other hand comes from H3PO4, which is a weak acid, which makes this a weak conjugate base. So this is going to be, so right here, if this is a base, this is going to be a weak conjugate base, so it's a basic salt. So whenever the anion is basic of a basic salt is available and it comes from a weak component, that means proton is going to react with this to produce phosphoric acid, and a reaction with proton is basically going to reduce the concentration of phosphate, so more and more silver phosphate is going to solubilize to produce or increase the concentration of phosphate based on Le Chatelier's principle. So it will again increase the solubility of silver phosphate because proton will react with phosphate to produce hydrogen phosphate ion in this case, right? Lastly, let's take a look at this example. So if I have a salt solution of silver chloride, solubility is again silver, produces silver ion and chloride ion. If we add more protons from the outside, why does it have no effect on solubility? So that's a first. Why? First thing is it does not affect the solubility. You should be able to figure out that. And then the question is asking why. So why is that? Remember, it only affects the solubility in case of basic salt. So the anion should be a weak conjugate base that is coming from a weak acid, right? So AgCl in this case, chloride ion is the anion. It's coming from HCl, which is a strong strong acid, which makes this a very, very weak conjugate base, which means this is not going to react with the extra proton that we add from outside. Only the basic salts or the weaker component react. So this is very, very weak. It's not going to react, which means you can add as much of proton from outside. This is not going to react with it. So the equilibrium will not be disturbed even if we keep on adding more and more protons or acid from outside. So the concentration is not going to be affected, so equilibrium will not be affected, therefore the solubility will not be affected in this case. So you should be able to identify the salts. For instance, there are a couple more examples here. So write balanced equation to explain whether addition of protons from a strong acid affects solubility of each of these ions. So each of these compounds. So the first compound is lead bromide, lead 2 bromide, meaning PbBr2, right? So in this case, what would be the equilibrium for this salt? It's going to be lead ion, Pb2 plus, and 2Br minus ions, right? So that's our equilibrium equation for the solubility of this salt. This is the solid, these are aqueous solutions. So if I add proton from outside, it's going to react with the anion, right? Now where is this anion coming from? This is coming from HBr, which is again a very strong acid, meaning this is a very, very, very weak conjugate base that will not react with our acid, so it will not be affected by the solubility of this compound is not going to be affected by addition of any protons from outside. Next salt is copper 2 hydroxide, so that is CuOH whole twice, which dissociates to give us copper 2 plus and hydroxide ions, 2 hydroxide ions. So in this case, what's going to happen is, where is this hydroxide coming from? This is probably coming from water, which is a weak acid, which means this is a weak conjugate base. So this is going to react with proton. So the reaction that the question is asking is, is that OH minus will react with proton that's added from outside to produce water, which is liquid. This is aqueous. This is aqueous. So if I add proton from outside, it's going to react with this hydroxide ion to produce water. So hydroxide ion concentration is going to be decreasing. Reaction will try to increase that by creating more of it. So it will go towards the right, meaning more and more of this copper hydroxide will become soluble. So it will increase the solubility of this particular salt. Right? That makes sense.